and independence. So conditional probability is what happens when one thing is already known and then you check the probability of another. So for example, the probability that some event B occurs, given that A occurs, has a certain notation. The notation for that is right here. The probability of B given A occurred. So they put a little vertical line in there to indicate that. And the way that you find it is down below here in this formula. So what you do is you take the probability of the intersection of A and B together, and then you divide by the probability of A, which is the event that has already occurred. So down below there's a two-way table. And we're looking at this homeowner and not a homeowner, and high school grad, not a high school grad, and taking a look at what's going on. So if we know that a person owns a home, what is the probability that the person is a high school graduate? And so we're supposed to use conditional probability to figure this out. And so when you write this down, we're looking for the probability that we are a high school grad, given that they are a homeowner. And in this case, we know that the intersection of A and B, so the intersection of the high school grad and homeowner, is the 221. So that's the probability of A intersection B. And then we want to know what's the probability or the outcomes of being the homeowner, or sorry, let's see, homeowner. Yeah, homeowner, which is 340. So your likelihood that you're going to be a high school grad, given that you already are a homeowner, is 221 out of 340. Using that same table with the conditional probability, if we know that the person is a high school graduate, what's the probability that they own a home? They're asking a different question in this case. So the probability that you are a homeowner this time, given that you are a high school grad, which is asking the reverse question. So now we look at the fact that you want to be both again, which is still 221. But this time, you want to find the probability of A occurring. So the thing is 310. 310, thank you, for the high school grad. So in this formula, when you look at probability of independent events, the previous event should have no effect on the current event. And as we look at what's going on here, you'll notice that whatever occurred as the event you're looking at, in the first case A, that should be the probability no matter what happened with B, and in the second case, B, being the first thing, should not be affected by the event A that already occurred, and that's why it's still the probability of B. So looking up above, and you look at the two pieces of information, when you look at those two things, are those the same thing? Are they independent or not? So if we look at being a high school graduate and owning a home independent, we could look at, for example, the probability of being a high school grad, given that you're a homeowner, should be equal to the same thing as being just a probability of the high school grad, if that's true based on the formula up above. So we look at these two things. So we did the high school grad and homeowner. That was the 221 out of 340. Wasn't that it? From up above. And the probability of being a high school grad, if you look back up in the table, we have 310 out of 500. Very good, thank you. 310 out of 500. And as we look at these two probabilities, what we notice is that they are not equal. And so we know that these things are not independent, because otherwise those two probabilities would be exactly the same. Okay, so sometimes it's very nice to model to see what's going on. Oftentimes when we do this in our class, we'll do it with things like medicine. Usually it's two events that are occurring, and we do a tree diagram. So the general multiplication rule, in order to show this thing happening and then using a diagram, is that when you're looking for the probability of the intersection of two events, or what's the likelihood that both occur, is the probability that the first thing occurs times the probability that the second occurs given that the first occurs. And that's what this information is showing right here. And a very helpful way to model that is using a tree diagram to show what's going on. So for example, in 2010, the Kaiser Family Foundation released a study about the influence of media in the lives of young people from ages 8 to 18. In our study, 17% of the youth were light media users, 62 were moderate users, and 21 were heavy users. Of the light users responding, 74% had good grades, 68% of the moderate users had good grades, and 52% of the heavy users listed their grades as good. What we're going to do is we're going to draw a tree diagram based on this. So the tree diagram would look something like the following. We have the students that we're talking about, and we had three different possibilities. And in these three different possibilities, we had 17% were the light media users, 62% were moderate, and 21% were heavy. And out of those light users, there were good grades and bad grades. So the good grades of the light users were 74%, which means that the remainder, of course, would be bad grades, so that would be 26%. Of the moderate users, we had 68% being good, which means 32 were not good. And of the heavy users, 52% were good, which meant 48 were bad. And then using the knowledge that these were the good grades and these were the bad in each case, we can see what each of these likelihoods is going to be by multiplying their probabilities. So in the first case, if you multiply them out, you get 0.1258. So if you want to report this out as a percentage, you could say 12.58%. The second percentage is 0.0442. You can find these by multiplying those two probabilities. The next one is 0.4216. And then 0.1984. And then 0.10. Or sorry, 10 is right the first time, sorry. 1092 and 0.1008. Now as we look at those percentages or probabilities of occurring, we want to know what's the percentage of young people that say that they get good grades. So if you're looking for the good grades, we would add up all the different good grade probabilities. So that would be the 0.1258, the 0.4216, and the 0.1092, for a grand total of 0.6566. And so this was adding up all of these grades. And so making sure that, of course, we read the asking question. It says what percent, so I should write that as a percent. So I would write down 65.66%. Again, always make sure you answer the question. So my 0.6566 was the probability, but they say what percent, so I answer in the percent. Okay.
I think your Darth Vader shirt on too tight.
Thanks for noticing. What percent of the youth with good grades are heavy users of media? So in this next question, you're looking for the probability that you are a heavy user given that you have good grades. So the heavy users with good grades, because remember you look for the intersection first, so the heavy users with good grades is 0.1092. And then that is out of the total good grades, which is 0.6566. So we know that the good grades is 0.6566, and the heavy users with good grades is 0.1092, for a grand total of 0.166. And again, we're going to write it out as a percentage, so we would say 16.6%. So intersection on the top, total possibilities on the bottom. And then the last one says, what percent of the youth with not good grades are light media users? So we would say, what's the probability of being a light user? And if you're Darth Vader, that'd be a lightsaber. Given that you had not good grades, which I would also call bad grades.
What does it mean to have not good grades?
I just believe I said that that's a rhetorical question. So then a light user and bad grades from back up above was 0.0442. And then the probability of having the bad grades would be everything else, so that'd be what? 0.3434? That's funny. Okay, and so for a grand 0.1287, or in other words, if they asked for the percent, you would say 12.87%.
No, we're not. Oh.